So today in class we started to review logarithms, like what they are, tried to wrap our head around them conceptually, and then use them to solve some equations. And so for this video I want to focus on a specific type of exponential model and a specific type of logarithm involving this exponential constant e. So even in first quarter we started to look at functions involving this base of e, remembering that e is a irrational number that's roughly equal to 2.71828, right? And it goes on and on and on, just like pi. So what we informally call this poked because it represents a model where we use a p naught as the initial value, right? Initial value. And then kt is our exponent, where t is time. And then k is some kind of like growth or decay. We'll just call it a growth or decay constant for now. And then we have that base of e. So for example, if we want to look at a function like p of t equals 50 times e to the 0.05 t, okay? This represents an initial value of 50, and this is representing exponential growth with a k value of 0.05, right? So this is a function where we're modeling exponential growth, and remember that we use e in models with continuous compounding, meaning that how quickly the amount is growing directly depends on how large the amount is. We talked about this a little bit quarter one, representing the populations, because the bigger a population is, the quicker it's going to grow, because the bigger your population is, the more people you have within your population to reproduce, right? So what we want to look at then with poked is how to use logarithms to solve equations involving poked. So first we need to define the natural log, right, which is just log base e. We covered logs with different bases today, and this is the log with the exponential constant as its base. So we just denote it as ln for natural log. So right, like e to the first is approximately 2.71828. So then log base e of 2.71828 is just going to be equal to 1. Right? Natural log of e is 1. E squared is equal to roughly this decimal, so if we do the natural log of e squared, that's going to be 2. Right? Remember how functions send inputs to outputs and inverses send outputs back to inputs. Here the input is 1, the output is 2.71828. Okay, so then if we put that output into the inverse, it sends us back to the input. Okay, here's our input of 2 and our output of 7.3891. So if we take that output and put it into the inverse, then we go back to the input of 2, right? So e cubed 20.088855, then we do the natural log of that value and it gives us just 3, okay? So what we can do is we can use this inverse function to solve equations where we have a poked formula equal to a certain output and we want to figure out what input goes with that output. So for example, we have this function 2000 times e to the 0.02 t. All right, we're not going to partner talk. I meant to take that part out. We're just going to talk through this on this video. So the question is, after how much time will the population be exactly 2,225 given this growth model? So what we're going to do is set this equal to 225 equals 2,000 times e to the 0.02 t, right? So we are trying to figure out what input goes with this output, right? This function sends inputs to outputs, so we're going to end up needing to use the inverse to figure out what input goes with this output. So what we can just do is we're just going to solve for t. So we're going to divide by 200 on both sides, or 2,000, sorry. All right, and then we can simplify this. So 2225 divided by 2,000 is 1.1125, and that is now equal to e raised to the 0.02 t. All right, so this is where we now need to apply our inverse, because what this equation is saying is e to the 0.02 t is equal to 1.1125, we don't know what this is, but we do know what this is, right? So if we're going to solve, we're going to now convert this to a logarithm, right? So it's going to be a log of base e, so natural log, okay, of 1.1125, and that's going to be equal to 0.02t. Because remember what a log is saying. It's saying e, that's our base e, we can't see it because we just write it as natural log e, to what power is 1.1125? Well, e to the 0.02t power is 1.1125, so that's what's on this side of the equation. So now if we want to finish this and solve for t, we can just divide by 0.02 on both sides. Okay, and then that is t value, and we can just plug this into a calculator, and we're going to get that t is roughly equal to 5.33 years. Okay, I forgot to mention that t is in units of years. All right, so there's our answer. Now what I want to talk about next is how we can actually approach this from a graphical sense rather than an algebraic sense. So what we can do is actually plug in our function to a graphing interface like Desmos or a graphing calculator and find where it intersects with the point 2225. So that's what I'm going to show you now. So what we're going to do in our Desmos cells is in the first cell, we're going to put our function, remembering that Desmos mostly just likes to work with variables like x. So we're going to do to the 0.02 times x instead of t, right? And that's going to graph our function for us. And then in the second cell, we want to put y equals 2225. What that does is it graphs a horizontal line at the y value that we're looking for, which is 2225. You can see that we have our graph of our curve, and then we can see where they intersect. We can see that at t equals, or I guess in this case it's x, 5.33, we have the output that we're looking for, 2225. And that's what we got when we did this algebraically on the previous slide. Now notice if you just plug this into Desmos right now as normal, you probably aren't going to see the graph because I had to adjust the window to account for the fact that this is a graph that has pretty big outputs, whereas Desmos normally just goes between like -10 and 10. So I'll show you how to do that in our next example, how to adjust the window to make sure you can see the graph. So we have another example. This is modeling the value of a car. As you might know, once you buy a new car, it immediately starts losing value as time goes on. So we're modeling how the value is going down, and the question is how many years will it take for the car to reach $70,000 of value, right? So we bought it for $80,000, a pretty expensive car here. And what we're going to do is we're going to set this equation equal to the value we want. So we want to get 70,000, right? And that's equal to 80,000 times e raised to the -0.05 t. So just like before, we're going to divide by 80,000 because we want to solve for t eventually here. So divide by 80,000. To make this easier on ourselves, we'll leave it in fraction form. But remember, we can just reduce this to just plain old 7/8. Just cancel out all those zeros, right? So now we have 7/8 equals e raised to the -0.05 t, right? So now we have to use our natural log again. So we're going to say the natural log of 7/8 equals -0.05 t, right? Because this is saying e to what power is 7/8? Well, e to the -0.05 t is equal to 7/8. So this is what our logarithm is going to be equal to. So to finish this up, we should divide by -0.05 on both sides. And that's going to give us our t value, right? We're just going to plug this into a calculator. Okay, plug it in. I'm getting t equals about 2.67 years. That is the value we're looking for. Okay, solved algebraically. But now we're going to look at this same problem graphically to check our answer. Okay, so here you can see I've given you more of the Desmos screen here. So I typed in my function to the first cell. In the second cell, I typed in y equals 70,000. And then you can see that there's the intersection point at that input of 2.671, sorry. All right, so notice how I changed the window. There's this little wrench up in the top right corner that pulls up this menu that you can use to edit your graph, right? So I knew from my algebra that my inputs are small because my answer is 2.671 here. So I just went ahead and made my inputs window kind of small, like 0 to 7, right? Now on the y-axis, you can see that I changed it from like 0 to 100,000. And this comes from the fact that my initial value is 80,000. So I know that I at least need to make a window that it's going to include 80,000. So I just went to 100,000 just to make it a little bit bigger than that. And now you can see if you change your window in that way, then you now have a graph that you can see, and you can see where your graph intersects with the 70,000 value that we're looking for. The last thing we're going to do is look at how we could solve an equation like this. And I first want to show what this is representing, right? So this R value is some percentage growth. Okay, in the context of time, we can assume that 12 is representing months. So we're applying this interest. We're applying this interest every month for 12 months, and we're seeing that that is leading to 8% growth. So the question is, how much interest do we need to apply each month in order to lead to an overall 8% growth in a year? We can solve this equation using logarithms. So I first want to point out that there's multiple ways we can approach this problem, and I'm just going to show you the power of logs, and one way we can do this actually using the natural log. So what we can do is we want to solve for r, right? And we currently have this 12 up in the exponent that would make this hard because this is 1 plus r raised to the 12th power. So what we can do is apply the natural log to this side of the equation because that's going to allow us to bring this 12 out front. Based on the rules we learned today, we informally call that the plog rule. But just like you've always done since you started solving equations in pre-algebra, if you do a mathematical operation to one side, then you have to do it to the other side of the equation to keep it balanced. Okay, so we have the natural log on both sides. So now that's going to allow us to bring our 12 out front. So we have 12 times the natural log of 1 plus r, and that's equal to the natural log of 1.08. So now we can divide our 12 over to the other side. So natural log 1 plus r equals natural log of 1.08 divided by 12. Okay, so now we're getting closer to being able to solve for r because we just have the natural log of 1 plus r. So we have to do the inverse operation of natural log to undo it on this side. So the inverse operation of taking a natural log is raising something to the from e to the power of that. So e to the natural log of 1 plus r on that side, and then we have to raise this side up to the power as well. So we have e to the natural log of 1 plus r equals e to the natural log of 1.08 divided by 12. So since e and natural log are inverse operations, we can just cancel this here. So now we have 1 plus r equals e raised to the natural log of 1.08 divided by 12. So then our last step here is just to subtract our 1 over. So we get r equals e to the natural log 1.08 divided by 12, and then we have to subtract 1. So we're just going to plug this into a calculator and see what we get. All right, I just plugged it in and I got r equals 0.006, and I'm actually going to write out the whole decimal here, 0.0643403 0.011. Okay, so what does this represent? Well, this is a decimal, right? So 0.6 would be like 60%. 0.06 would be like 6%. This is 0.006, which is about 0.6%, right? 0.6%. So what this is saying is about 0.6% interest per month will lead to a total of 8% interest each year. And how we can just check that is we can take this R value we just got and we can do 1.006. I should make that 0 look more like a 0. 0.0643403 0.11, and we should raise that to the 12 power to do it each month, and that should give us the 1.08 that we were looking for. Okay, that's all for now. Nice job.